Hi, in this video we're going to be talking about a concept called efficiency in thermodynamics. Efficiency is one of the most frequently used in thermo. It indicates how well energy conversion or transfer process is accomplished, right? So it's efficiency normally using performance efficiency is called performance or eta in Greek letter. Is desired output over required input. Okay, desired output over required input. Let's take a look some of real life example. If you have a water heater, regardless is gas or electric, if it's gas, and so it's going to be the heat supplied the heat that's required by the gas burning, right? So that's going to be the required input. But what's the desirable output? It's you want to go ahead and have that hot water, the water heated, right? So then there will be efficiency there. Another example is, for example, you have an electric fan and it's 50 watts and it output mass flow rate of 0.5 kilogram per second, and with velocity change from at the beginning still nothing turning to turning speed of 12 meter per second. So that's like a kinetic energy increase. That's energy increase. And that's what you desired, right? You desire the fan speed to go up. That's your output. And if you calculate that, half mv squared, and here m is m dot, it's mass flow rate. So you're gonna get watt. So half m dot v squared, that give us half mass is 0.5, velocity is 12. And that will give us the output. So with half m dot v squared and the required input is 50 watts electrical, right? That's going to be electrical turning to the shaft turning 50 watts. Then that can help you try to calculate the efficiency. Here that's the symbol eta. That's the efficiency symbol. Okay. So in all, efficiency can be just described as desired output over what's required input. Now, let's look at some other example. For example, you have a heat combustion chamber. What do we desire? We desire amount of heat released during combustion, right? You want to have that as much as we can. You want to have a lot of heat released. But what's required to do that? We have to burn the fuel. And so there's a heating value of the fuel burned, and that's required for us to get the heat to release out. So knowing this, you can find combustion chamber heat efficiency eta here. And how about the light bulb? That has efficiency as well. What do we desire? We want to have a lot of lumens, which means a lot of brightness. So that's our desired output. And what's required? We're going to have electrical work. So that's watt. Okay, that's required. So it's output, desired output lumen over required electrical work. That can calculate the efficiency. Now let's look at a kitchen appliance. If you have this electrical pot and that has given the input as 5 kilowatts, but however only 3 kilowatts of that energy is used to cook the food. There are 2 kilowatts inevitably it's released to the surrounding that kitchen, because whenever we cook in the kitchen you always feel like the room gets hotter, right? Because it's not all of this heat has been converted to cook the food. And so in that situation, your desired is 3 kilowatts and your required input is 5, then therefore efficiency is 0.6 or 60%. Now let's look at some other examples. And this one is turbines and compressors. So in turbines, here's the example for turbine. Turbine is like is this device where, for example, you have superheated vapor, you know, it's coming out of boiler, and they are going to go through this turbine, and this turbine has a lot of those blades in there. And when the superheated vapor going through, it's going to turn those blades, therefore turn the shaft. Okay, so in other words, the thermal energy is converted to the mechanical energy. So then you have this turning shaft turbine. And normally at a power plant, turbine is connected to, the shaft is connected to inside the magnetic coil. That's where generator is, right? When you have something turning inside the magnetic coil, then it's going to generate electricity. Then, so turbine is that energy is extracted from this liquid. This liquid basically is a superheated gas. So the energy is taken from there and changed to this mechanical work turning the shaft here. And opposite to turbine, it's compressor. For compress, you have to add energy, right? You have to put energy in to increase up the pressure of the fluid. And the compressor, you can have substance to be liquid, and that will be pump. You know, you increase the pressure of the liquid. If your substance here is the gas, then that's basically a compressor. So compressor and a pump, they basically are same device. They have the same purpose, is trying to increase up the pressure. The only difference is compressor dealing with gas, pump dealing with liquid. That's the only difference. So here you learned 3 different devices. Turbine. Turbine is trying to generate work. And however, compressor, you requires work to increase up the pressure of the fluid. Okay, so knowing that will help us to understand this. Understand about motor and pump. So pump, the goal, what's our desirable output of pump or compressor? It's trying to increase up the energy, mechanical energy of the fluid. That's our desirable output, our goal. And however, what's required for the pump? Remember, in order to pump something here or compress something, you have to have energy added. So in that situation, the mechanical energy input, that's required. So therefore, the pump efficiency or compressor efficiency is going to be delta E, mechanical fluid, mechanical energy increase of fluid over the mechanical energy input for the pump. So knowing that, that's the equation. Now let's understand the motor, how motor work. And here motor is electrical motor. Okay, so when you plug it in, so you require electrical power input. And what do we desire for motor? We want to turn, right? We want to have mechanical power output. So that's very intuitive. So that's going to be mechanical power output over electrical work. And often the motor and pump is connected. They are coupled. So they are in a tandem fashion. In other words, you have a motor first, and then you have a pump. Why do we do so? Because you plug the motor, so you have electrical output, electrical power input. It's gonna turn. It's gonna have mechanical power output, and that mechanical power output of motor happens to be the input of the pump. Okay, and then once you have the input, mechanical input is going to increase up the mechanical energy of the fluid. So that's why they are coupled together. In that situation, when you have a motor pump together, what's the overall efficiency? Then you're going to think about what's ultimate goal here. You want to increase up the mechanical energy of the fluid, right? And what is most initial input source? That's going to be the electrical input for the motor. So that's going to be the equation for that. Okay. Another example of this coupled devices are the turbine and generator. So now we talked about turbine earlier. Turbine is going to have this fluid, for example, superheated vapor coming, and they decrease energy. In turn, you turn this shaft. So that's going to be our desirable output, mechanical energy output. And input is going to be mechanical energy decrease of the fluid. So that's how turbine efficiency work at a turbine here. Then how does generator work? Generator is this shaft is turning inside the magnetic coil. In turn, we got our electricity. So desirable output is electrical power, and required input is this mechanical power input, this shaft turning. Now when you then understand generator efficiency will be this formula right here, right? Electrical output over shaft coming. Then however, when you put turbine and generator coupled together, what is this overall efficiency? Then think about, what do we want at the ultimate end? What's our ultimate goal? Electricity. So that's electricity output. And what do we desire from, what do we require from very beginning? We need this superheated vapor comes into the turbine, which means the decrease of the mechanical energy of the fluid. So that's our overall efficiency, okay? Now I'm actually going to challenge you and to look at this. So I want to look at this overall. For example, we said that this turbine connected to this generator. If you look at this box together, your ultimate output is electric work. And ultimate your required input is going to be decrease of the mechanical energy of the fluid. So that's going to be our overall. For turbine generator, it's going to be electric output over decrease of mechanical energy of fluid. However, what we're about to discuss here is this has a different formula, but it's also, we're talking about turbine efficiency is the mechanical energy, the shaft that's turning, shaft. And in order to do that, we need a mechanical decrease of the fluid. Then the generator itself, efficiency will be electrical output, which is desired. And in order to do that, we need to have a shaft that's turning inside. Then the reason we are doing this is if you are going to times the turbine and generator efficiency together, what do we notice? This shaft work is gonna canceled. So essentially you get electric work over mechanical energy decrease of the fluid. So this happened to be what? This happened to be the same as that. Then we get another formula. The overall is basically the product of each individual efficiency. So knowing that relationship, we can even look at this problem. We are given each individual efficiency, 0.75 and 0.97 for turbine generator. When we times them together, we got this overall turbine generator efficiency. All right, so that's the efficiency concept. Hopefully that's clear. All right, bye.